Okay, hello everyone. This is Volts for April 23, 2025. What's up with hydrogen electric aviation? I'm your host, David Roberts. Aviation is one of the few remaining sectors that can fairly be characterized as difficult to decarbonize. At the very least, we're not entirely sure yet how we're going to do it, or if we can do it at all, which is one reason some people say the only solution is to fly less. Lots of people inside and outside the industry are betting on sustainable aviation fuels, or SAF, made with some mix of electrolyzed hydrogen and captured carbon, though such fuels remain extremely expensive and comparatively rare. But some people, my people, the Volts tribe, are betting on electricity. For instance, in June of last year, I spoke with Kyle Clark of Beta Technologies about his battery electric planes and electrical vertical takeoff and landing aircrafts, eVTOLs. Today's guest, Val Miftakhov, has a slightly different approach. His company, ZeroAvia, makes engines rather than planes. Except they're not engines exactly because there's no combustion. Instead, the powertrain consists of hydrogen fuel cells that generate electricity and electric motors that use that electricity for propulsion. For now, ZeroAvia is swapping out engines in existing planes. Soon it hopes to see new planes designed around electric aviation. And beyond that, it envisions redesigning the U.S. flight system around more smaller airports, shorter hops, and ubiquitous hydrogen refueling. I am excited to talk with Miftakhov about all of that. With no further ado, Val Miftakhov, welcome to Volts. Thank you so much for coming.
Thank you for having me. Great to be here.
So, as I understand it, the engine, I'm using, for the purposes of this pod, all uses of the term engine should be heard in air quotes, right? So, your engine consists of three parts, basically. You've got hydrogen storage of some kind. You've got hydrogen fuel cells that use the hydrogen to create electricity. And then you've got electric motors. So let's start with the fuel cell because, as I was thinking about this, I suspect most people, even a lot of energy-inclined people, don't really have a great sense of what fuel cells are. So could you just explain quickly how a fuel cell creates electricity?
Absolutely. And by the way, the confusion goes both from the general public, but also from the aviation folks sometimes as well, because in the standard aviation terminology, fuel cell is where you put fuel in the aircraft. So we've got a lot of those as well. But overall, fuel cell is an electrochemical device that takes some chemical, energetic chemical like hydrogen, but there are other types of fuel cells out there, and oxygen, typically from the air, and converts that in a electrochemical device into electricity. Point of note there is that there is no, as you said, combustion, or there is no moving parts associated with it. So it's really looking more like a battery with a number of cells arranged in a stack. And then you get a fuel cell stack that produces a large amount of electricity at relatively high voltage, so similar to a battery pack. But of course, with the fuel cells, and especially with hydrogen fuel cells, at the system level, you get much, much higher energy density or specific energy in terms of amount of energy per unit of weight of the system.
Well, I want to return to that in a second. So just on a kind of first principles basis, why fuel cells instead of SAF? Why fuel cells instead of combusting synthetic fuels? What's the advantage?
Yeah, very good question. And the advantage comes from two sides. One is on the impact of why we're doing this altogether. Why do we care about moving to sustainable fuels or moving to new aviation? Yeah, we're talking about a couple of things there. One is pollution, of course, which has multiple elements. So carbon is one, but there is also non-carbon effects on the climate and on health. There are a lot of studies that put, without any doubt, adverse health effects around the airports because of the particulate emissions, because of the high NOx output, nitrogen oxides from the combustion from those engines. And in order to get away from all of that, you really need to get away from combustion. So as long as you're burning fuel, you're still having all of those negative effects. So you can burn zero carbon fuel, you still have those effects.
You still have the particulates and the NOx and the other kinds of air pollution.
That's right. And, there are other negatives of combustion, of course, because you have high temperatures and pressures, your materials are stressed, and as a result, your maintenance costs are higher. But those are sort of softer effects. The hard reason, at least for us at ZeroAvia and similar pioneers out there and people who support us, like Breakthrough Energy Ventures, Amazon Climate Pledge Funds, people who really try to force the transition of hard to abate sectors, these combustion effects are really, really important. So that's one aspect of things. The second aspect is that sustainable aviation fuels that are based on synthetic hydrogen production and carbon capture, as you mentioned in the beginning, those are fundamentally much more expensive than hydrogen fuel cell propulsion. Because you can use, with hydrogen fuel cells, you can already use that green hydrogen that you produced without going through carbon capture, without going through the chemical plants architecture that combines that hydrogen with carbon and produces liquid fuels. You can use hydrogen directly in the fuel cell system, and you can use it more efficiently because the fuel cells, the current generation of fuel cells, already are 60% or so efficient. And the best combustion engine we have for aircraft, the largest engines that we have, are about 50% efficient. But vast majority of the engines on the smaller aircraft, under 100 seats, are less than 30% efficient. So you have double the efficiency. You don't need any of the carbon capture or any of the chemical process beyond it. So economics becomes much, much better. So these two factors, we think, undoubtedly, to us at least, points to hydrogen fuel cells as the eventual solution to this problem.
So A, you're getting more energy out of the clean hydrogen you produce just because you're not sending it through elaborate chemical reactions and creating some new fuel out of it. You're just using it directly. And B, no pollution. And as far as we know, this is the only genuinely no pollution flight option that we have, right? I mean, any combustion basically entails some of these particulates and NOx, et cetera, right?
Yeah, that's right. And, hydrogen combustion is obviously cleaner than hydrocarbon combustion because you don't have carbon in the chain. So you might not have particulates, but hydrogen burns hotter. So anything that burns hotter produces more NOx, right? So there are disadvantages there. Yeah. So electrification is really the only what we call true zero emission option. Yeah. Now we've done the end-to-end sort of life cycle analysis as well, and there is, of course, you need to produce engines, so there is some emission in that potentially. So the total abatement is anywhere sort of around 95%.
Wow.
Of the climate effects.
And all that remaining CO2 is in the embedded CO2 of the manufacturing process. There's no
Correct.
CO2 at all in the flight or the operation.
Yeah, and theoretically, this is calculated using the current sort of energy intensity and energy composition of the manufacturing processes. If we eventually move to 100% renewable energy-based manufacturing and extraction of the some of the minerals that are required for building the fuel cells, maybe we could get to 100% abatement, right? And that's the beauty of these technologies, kind of similar to the electric cars, yeah?
Right. Yeah.
Our grid is not obviously 100% renewable right now, but it's getting more and more so. So you put installed base of these engines, of these motors out there, those cars, and it gets cleaner and cleaner and cleaner over time.
Second fundamental engineering question is then why fuel cells instead of batteries? You sort of mentioned just has a higher specific energy, but in specific energy, as I understand it, is just the amount of power you can get out per weight. Is that right?
Yeah, energy per weight. And, maybe some history for, myself before I started ZeroAvia. I was running a company called Electric Motor Works before ZeroAvia for about 7 years. And what we built there is the world's largest network of smart EV charging stations. So I was involved with electric car industry quite a bit. I had, in addition to the large network of charging stations, had relationships with 10 plus automakers, controlling charging of the vehicles, energy flows directly, controlling the batteries and battery management systems in the cars. The point I'm making is that, through that work, I got pretty exposed, or our team got pretty exposed to all the challenges of the battery technologies and how quickly it can evolve. And when I started ZeroAvia, I think there are 60 projects out there, 60, of various novel aircraft ideas that are all based on batteries. And people were telling me that, hey, well, this hydrogen thing doesn't make sense because in 5 years, we're all going to be flying on batteries hundreds of miles because they're going to become 5 times, 10 times better.
Right. Everybody's betting on batteries continuing to go down this curve, right? Cheaper, 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 more and more energy dense.
Yeah, and cheaper, 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 I agree with, right? Because that's an easier thing to get, right? You go you go higher volume, you increase extraction, you optimize processes, you put robots everywhere, right? The cost can decrease quite dramatically. But the energy density, or specific energy to be precise in the terminology, right, per unit of weight, is very hard to move. This is a electrochemical problem, and there are a lot of the trade-offs, and there are theoretical limits. So in the beginning, when I started ZeroAvia, we did some modeling of what would absolutely ideal battery do if there was such a thing, right? And the way you do it, or the way we did it, is we said, okay, what is a battery? The battery is something that has anode, cathode, and there is charged ions moving between them. At least that's how we understand the battery for the last 100 plus years. Okay, and what can be the lightest carrier of that charge? You need a metallic ion. The lightest metal is lithium, so that's the absolute lightest possible ion carrier. If you just take the mass of the lithium atom and calculate the energy, maximum specific energy, just based on that, you end up somewhere around just over 10,000 watt hours per kilogram. So no battery can theoretically ever be close to that number, okay? And that's before you think about anodes, cathodes, all the electrolyte, all the material around it.
That's just the weight of the lithium itself.
Exactly. And you have to divide it at least by a factor of 3 to 5 because you have anodes that has to, accept all those ions, and cathode, the same thing, right? Because these things do move around and they need to be mechanically stored somewhere. So all those things. And then you look at hydrogen, for example. It starts, chemical energy of hydrogen per kilogram basis is 33,000 watt hours per kilo. Okay? So you already start at 3x relative to the maximum possible theoretical, which is actually not achievable. And then you say, okay, well, clearly these things will never meet because they can't. Yeah. So hydrogen going into fuel cells will always be better. And then you look at the current state. Even back in the day, I was looking at the hydrogen versus the then state of the battery. You look at the current state, and we're still, depending which generation of battery you use, you're anywhere between 30 and 50x delta on the specific energy output. And yes, batteries improve single digits per year in the specific energy, but 30 to 50x is a big gap to close. And we know that it cannot be closed fully because of the theoretical limitations.
Okay, so this is why hydrogen instead of batteries. A quick question just about form factor. So you're taking sort of existing small planes, as I understand it. You're starting small and just taking out the old engine and putting one of these in. So I'm a little curious about the form factor. Like, do you cram these parts together into something that is roughly the shape of an engine? Like, does it look like like if I was looking at it, would it look like an engine to me?
Yes and no. Some parts would, especially the ones that connect to the propulsors,
Mm.
propellers, for example, in small planes. Yeah, so we need to rotate those propellers. They're located in a certain place, either in the nacelles or the front of the aircraft. The motors will look similar, and they will be in a similar place. The rest of the system, we have the flexibility to place it elsewhere, and we do.
The fuel cells and the hydrogen storage are somewhere else in the plane.
That's right. They could be.
Right.
Typically, in the existing aircraft, it's hard to find place for the fuel cells in the same place where there is engine today. Partially because, fuel cells still take a little bit more space, but also for some of the vehicle weight optimizations, we're still heavier than the turbine engines. So center of gravity issues, weight and balance on the aircraft need to be taken into account. So for the existing aircraft, we tend to have to separate the fuel cell system from the propulsion system.
So, what is the current plane? Like, what do you have that can run a current plane? And then, sort of like, what's next? When we're talking about sizes and classes of planes, just talk about like what you can do now, what's next, and like what's the target.
Of course. So the exciting part, I start from the end of your question. The exciting part of this technology and this approach is that it can, over time, be applied to any size of the aircraft that we have today.
I read the white paper and I want to talk about some of those innovations that would be necessary here in a minute, but let's just talk about like what we can do now.
Yeah, so that's the exciting bit, and that's what excites me, our team, our investors, right? Because we don't want to be working on something that can only affect the small aircraft, because that's a relatively small portion of the market. That said, we are very pragmatic. We start with the first application in the smallest aircrafts that is commercially meaningful from the market perspective, market size perspective, and that tends to be aircraft 10 to 20 seats in size. That's powered, generally speaking, by engines at around 1,000 horsepower. Okay, and 10-seat aircraft tend to have one of those engines. 20-seat aircraft would have two of those engines on the wings, and that's our first product. So the first product is around 1,000 horsepower. We have flown a number of variants of it. It is now in final design, submitted for certification about 15 months ago, and we're in the middle of our certification work right now.
So I can't quite yet bring my plane to you and have you swap it out. That's waiting on some final stamps of approval.
Right. Well, you can, but you won't be able to fly it commercially.
Right.
So we of course have flown a number of these engines in different aircraft. So they work. We know how they work. We have done the integration in several airframes. But in order to operate them commercially with passengers inside and paying cargo, we need to have the stamp. Yeah. So we are working on getting that.
And so for listeners' benefit, like a 10 to 20 seater plane, how big of a chunk of aviation is that? And B, what do those planes do? What are they used for?
Yeah, so in terms of the size of the market by dollar amounts, this is probably less than 1%. By total number of aircraft in commercial service, this is between 5 and 7% of the total.
Got it.
Yeah, because there are fewer seats, right? You have more planes, but the revenue is lower on a per plane basis. So today, these do, for example, cargo, this package delivery in less dense locations, or passenger transport in smaller airports. So, for example, some of the vibrant use cases for that include island networks. Like one of the largest fleets of 20-seat aircraft, for example, is deployed in Maldives.
Oh, interesting.
Yeah, over 100 aircraft flying there, and nothing else can really fly there, at least to the smaller islands, because there are no runways to take jets.
Yeah, I think we have some, if I'm not crazy, I'm pretty sure we have some of those in Seattle, just doing short flights like up to Victoria, BC and things like that.
That's right. Absolutely right. And, in general, especially in BC, the coastline beyond Vancouver is pretty rough to go around. So there's a lot of small aircraft activity going on. And then you can go even more extreme. And if you've been to Alaska, for example, right, everybody's flying because the roads are not as easy to traverse.
Yeah.
Hawaii is a big area as well for these types of planes, again, for the same reason. Yeah.
So there's a market, in other words, for you to get running.
Absolutely.
Get running on. So then what's the next class up?
So the next class is larger propeller planes. So these are some examples, two manufacturers really, mostly. ATR, which is a 50% joint venture between Airbus, who everybody knows, and Leonardo, an Italian manufacturer, probably not as many people know, but ATR is the largest manufacturer of these large propeller planes. They have a 40-seat variety and 70.
40 to 70.
Yeah, 40 to 70. And then there is a de Havilland Canada Aircraft Corporation that makes today up to 80, I think up to 80-seat aircraft called Dash 8. And those aircraft are our next target. And that's the engine that generally produces about 3,000 to 5,000 horsepower. And we have demonstrated already ground operations of components of that engine on the systems that we took from one of these 80-seat planes. And that was a project together with de Havilland Canada and Alaska Airlines, who's one of our investors and partners as well. So for the small engine, 10 to 20 seat, we finalized the design. It's now in certification. We're hoping to push it in service, in commercial service next year, 2026. For the larger engine, it's now in development, prototyping. We go through iterations, and if everything goes right, we'll submit it for certification in the next 2 years.
Mm-hmm. And that'll be the 40 to 80 seaters.
Right.
And what are those used for? Are those passenger planes mostly, or are they just larger cargo? Or
a little bit of both. We have some exciting discussions actually with some of the cargo carriers to help them expand their cargo networks with these smaller planes. For them, it's smaller planes because they fly jets today. But they want to improve the fast delivery of goods and packages to smaller locations, smaller metro areas. And this is how you do it, again, because a lot of those locations cannot accept large jets.
Right.
And similar on passenger. And a lot of these aircraft are used today. So in terms of the markets, this next size propeller planes, in terms of the dollar amount, this is probably 3 to 5x the market of the small planes.
But still, both combined, relatively modest.
That's right.
Compared to what I'm guessing is the next class up, which is the big ones, right? Or is there a middle class I'm missing?
Yeah. There is a middle class today. Regional jets. Yeah. So these are the two manufacturers. There are Mitsubishi Heavy Industries regional jet, formerly Bombardier. So this is the class or brand of the aircraft called the CRJ regional jets. There are about 1,500 of those in operation worldwide. And then Embraer is probably more familiar, and they have well over 1,000 as well. So these are regional jets. These are generally under 100 seats in size. They fly faster than propeller planes, and that's why operators like them. And that's the next segment. So we started some work with some of those manufacturers already, but no hardware yet. But that will be the next segment. And the segment after that is the segment that has majority of the dollars right now in the market. And that's called single aisle aircraft or narrow body aircraft. The examples, classic examples are Boeing 737 and Airbus A320 or A321.
Right. These are the ones people will be familiar, have flown on.
Yeah. Well, I think most of people who are flying will have flown as well on a regional jet on one of the Embraers from time to time. But most of the time today, if you're boarding the plane, you're probably boarding a single aisle aircraft.
Right. And so those two upper classes, some pretty big engineering advances are going to be necessary to get there, which I want to discuss in just a minute. But I got a couple of questions first. A couple of things about these existing engines. One is, I know from the EV space that electric motors require much, much less maintenance than combustion motors, just because you're not trying to control a bunch of explosions and toxic gases. There's fewer parts, fewer moving parts, fewer rotating parts, et cetera. Does that extend to hydrogen fuel cells as well? Like, is this package much lower maintenance than an equivalent combustion engine?
Absolutely. It's exactly transferable, that logic. Yeah. So we, again, use electric motors. So there it's directly transferable. And the fuel cells, also no moving parts. There are some moving parts, most notably a compressor, air compressor, because the fuel cell is an air-breathing machine. So it needs to have high-pressure air delivered to it.
Mm-hmm.
So you have to have a compressor, which is a rotating, but the compressor itself is an electric motor connected to a turbine. So it is also quite reliable. As a result, you have maybe a couple of moving parts in the system, like a motor and a compressor, and then everything else is non-moving parts.
And also not hot.
True. Yeah. Great point. Which has some strong additional advantages.
Mm-hmm.
Yeah. For example, because you don't have combustion, you generally don't have noise as well.
Right.
Because combustion is very noisy.
Same for EVs and transferable from EVs.
Absolutely right. You have the same advantages as you would have from the battery electric drivetrains, but you have more energy that you can carry with you. And by the way, I think the right tool for the right job. And I think electric propulsion is perfect for cars, for ground transportation, electric being battery electric, for ground transportation, especially for smaller vehicles.
Right. So you're not pushing hydrogen vehicles. A lot of people in my audience love to hate hydrogen cars. So you're not, it's purely an aviation thing for you, right? You think batteries can handle most of the other stuff.
Exactly. In fact, it was quite annoying to have to unpack or undo that damage that the car industry, some of the car industry did to hydrogen in general, because they, as I call it, they started from the absolutely wrong side of the hydrogen story. They went into light consumer vehicles, which is the worst place to apply this to.
Yes.
Right? Because you want to apply, like, why would you do hydrogen? Because it is more complex than battery electric, okay?
Well, also, and we're going to get to this later, but like genuinely green hydrogen is still pretty expensive. Like what is the analogy someone said about when they talk about using hydrogen to heat homes?
Mm-hmm.
He's like, that's like pouring champagne into your municipal water supply. You know what I mean?
I like it.
Green hydrogen is rare and expensive still, so you want to use it wisely.
Exactly. So if you ask yourself, okay, I have battery as an energy source and I have hydrogen fuel cells as energy source, how do I think about like relative application of the two?
Mm-hmm.
The way you would do it is you would say, okay, which types of, in this case, transportation require higher specific energy, like more energy on board the vehicle.
Right.
And you look at, let's say cars, for example, personal cars. And you can approximate this variable by, in the standard fuel vehicles, what percent of the vehicle mass or weight you have in fuel. Like fully loaded, fully fueled, what is that percentage? If you look at personal vehicles, small cars, that's 2 to 3% of the vehicle mass goes into gasoline, okay? If you look at 737 MAX, up to 40%, 40% of the vehicle can go into fuel. So this is 20x difference already on that dimension. And then you say, okay, what else, right? One other dimension you can use is you say, okay, what percent of overall, let's say 24 hours in a day, that vehicle is moving or using that fuel, right? And again, personal car, 95% of the time it sits somewhere and it's not moving. A typical commercial aircraft, especially regional aircraft, they're used more than 50% of that 24-hour period. Then you say, okay, well, the higher the energy utilization and the higher the vehicle utilization, the more hydrogen is applicable versus battery, because you need a lot more energy. So
You just need more energy on board.
that's right, you need more energy on board, and you cycle through that energy quicker, which means you may need even more energy on board per unit of time per day, for example, and you need to recharge or refuel much faster. And you look at different types of transportation, and you will clearly see that the consumer vehicle is absolutely the worst for hydrogen
Yes.
versus battery,
Yeah.
and the commercial aircraft is absolutely the best.
Yeah.
Yeah. So that's why we were like, hey, the whole market started from the wrong place, and as a result, it got all this bad rap because it's just not something that you should start with. Eventually, maybe we'll get to that point when we have all the airports with hydrogen, all the heavy duty long distance trucks maybe fueling in the same locations, and the hydrogen network gets developed, everything is done, and then maybe you can plug in also these types of uses like small cars, but not from the beginning.
Right. So on the maintenance thing, give us a comparison for if I have an combustion engine in my 20 to 40 seat plane, how long is that engine going to last versus how long one of these systems would last?
Yeah, so I'll give you a comparison for the first segment, which we have studied quite a bit, and we already, we are now in certification, so we haven't deployed any of these in commercial service, but we sold about 3,000 engines already to the operators, pre-sold.
Oh, so people are ready to go with these once it gets the final approval.
That's right, because, the biggest reason for this pipeline, if you will, of orders is because we can drive better economics. And most of the economical advantage comes from maintenance.
Mm-hmm.
Maintenance is a big source of operating costs for these operators. Part of this cost is direct, right? So you need to maintain, you need to replace parts and all of that. But the big part of the cost is downtime, service downtime. That you have to take if there's anything wrong with the engine, you need to repair the engine, but also the airplane sits on the ground not doing revenue work, and the operator loses money. So maintenance is a large part of the operating cost implication there. And we're able to reduce that maintenance cost and downtime by 2 to 3x for the operator. And that's a huge advantage. And that's one of the primary reasons why operators are putting these orders in, because we're able to communicate and show, frankly, based on already our engine operating records and the fuel cell and the electric motors operating records, that will be much better. To give you some examples on the 10 to 20 seat aircraft, the engines that are operating today, small turbine engines, have major maintenance intervals at around 2,000 hours. And complete engine overhaul, which means that you basically have to rebuild the engine or replace the engine, at 4,000 hours of operation.
Oh, it doesn't seem like that much.
It's not a lot. It's not a lot for a regional aircraft that is in the reasonably frequent operation. That's about a replacement of the engine every 3 years.
Oh my gosh.
Okay, so a typical aircraft, commercial aircraft, airframe itself lasts for 30 years. That's kind of the average. So imagine you go through 10 sets of engines. You can go through 10 sets of engines on that aircraft. So maintenance on the engines is a big deal for the operators. With the fuel cell system, fuel cell electric, we can go up to 10,000 hours between the major overhauls. And major overhauls are not as dramatic because the electric motors will last for the duration of the airframe, for 30,000 hours. And I'm sure Kyle told you all that already.
Yeah.
So then we're back to sort of the automotive analogy where you don't expect to change the engine on your car, right?
So is it when they do need maintenance or when they do break down, is it the fuel cells that are usually the source?
Yeah, so and it's not a breakdown, it's more of the degradation of the fuel cell.
Mm,
Yeah, and we'll see what happens with batteries really in aircraft as well, because in cars, I think by now, especially Tesla has shown that the batteries can last the duration of the lifetime of a car as well. But in aircraft, they're utilized much more thoroughly, yeah, if you will. So we'll see how that goes. But for fuel cells, this is degradation, gradual degradation of the fuel cells, and then at some point you cannot produce maximum power anymore, and there is a certain margin that you certify with, and
right,
you
right.
eat into that margin, and at 10,000 hours you say, okay, well, now you need to replace the stack.
I'm curious how sort of modular all this is. Like, can you pull an individual fuel cell out and replace it, or what? How chunky is this?
Yeah, very good question. So it is modular. Giving you an example, for our 600 kilowatt engine, or this 1000 horsepower engine for 10 to 20 seat aircraft, it has 8 stacks in it, arranged into 4 pairs.
Mm-hmm.
So a pair is a module right now. So we can replace on a module by module basis, and those are even the design of the integration of those modules into aircraft is done with maintenance in mind, so that you don't have to, take apart the whole thing in order to pull this out, right? You can just unbolt a few things and undo a couple of connections, and you can swap it in the field.
Mm-hmm.
So you don't need to have a huge downtime on the aircraft. The strong benefit, additional benefit, is that because you can make this system so modular, it's much more reliable, right? Because you have automatic redundancy.
Right.
Versus a typical single engine aircraft. If something goes wrong with the engine, well, you now have a glider. Yeah.
Right. So better failure modes than
That's right.
than combustion engines. Interesting. I want to talk about, one of the most interesting aspects of all this. So, as we've said, you've got the 10 to 20 seater engine almost ready to go, almost in commercial use, probably later this year, maybe?
No, next year, 26.
Next year. And then you get the 40 to 80 seater next. But then, as you say in this white paper that your company has put out, going to that next class up, the regional jets and higher, is going to require some big engineering advances. And so there are 3 basic components here. There's the hydrogen storage, there's the hydrogen fuel cell, and there's the electric motor, all of whom are going to need to advance in fundamental ways. And there's a line of sight to pushing them forward. Very, very interesting. So let's start with the hydrogen. So right now, hydrogen has good, what they called gravimetric density. It's very light for the amount of power you get out of it. That's a real advantage in flight. But it has very poor volumetric density, which means it's very diffuse. It's like it takes up a lot of space if it's a gas, right? And that's what you're using now as gaseous hydrogen. So it says in the paper, if we want to get enough hydrogen on board and have a manageable space for it to occupy a manageable amount of space, you have to go to compressed liquid hydrogen. Is that accurate? Like, what is the leap there from gaseous to liquid? What's involved in that? Hey there, everybody. Don't worry, I'm not going to tell you about a new mattress or push a credit card on you. This isn't an ad. There are no ads on Volts. It is supported entirely by listeners like you. If you'll indulge me for a second, I'd like to ask for your support. I started Volts because we're all surrounded by depressing news about climate change and misinformation about clean energy, and it's never been more important to share the stories of the real people on the ground doing the real work of transition and all the ingenuity and courage and public spirit they are bringing to it. People are hungry to hear these stories, to learn from and find inspiration in them. I've heard from people who changed majors or careers after hearing episodes of Volts. People using it in classrooms and community groups, even state legislators who have passed bills inspired by specific episodes. Sharing these stories matters. It makes a difference. If you have found value in it and want to help me continue doing it, I hope you will join the community of paid subscribers at volts.wtf. It's about the cost of a cup of coffee a month. If you don't like subscriptions, you can make a one-time contribution, leave a review on Apple or Spotify, or just tell a friend about Volts. I am grateful for any and all support. If you're already a paid subscriber, thank you. And now, back to the show. What is the leap there from gaseous to liquid? What's involved in that?
Yeah, you have to go to liquid hydrogen. You're exactly right. And the challenges with that, well, it is kind of rocket science. I was going to say it's not a rocket science, but it is kind of rocket science because the largest use case right now for a liquid hydrogen is in rocketry, rocket engines. But there is also significant use in the industry. In fact, even in the ground-based vehicles, most of the deliveries today from the production sites to the fueling stations on the ground are with liquid hydrogen because of the volume on the roads.
Just a quick question: if you get liquid hydrogen, do you then have volumetric density in the neighborhood of jet fuel? Like, what's how close can you get to matching the volumetric density of jet fuel?
Yeah, very good question. Not quite. You're still on the chemical energy basis. You're still about 3.5 times more volume for liquid hydrogen.
Got it.
Now, when you sort of account for the difference in the efficiency of the engines, because the back to the beginning of our conversation, combustion efficiency is much lower than the fuel cells. So when you account for efficiency difference, you're about 2x more volume.
So that gets you a little, some of your volume back.
That's right. But you're still twice as much. So
right.
Which the other way to say it is you can get half the range with the same volume.
Got it.
Okay. And in order to kind of move away from that restriction, that's when you start talking about new types of aircraft design that has more volume for hydrogen. And good examples of that are, I don't know if you're familiar with a company called Jet Zero down in Los Angeles, for example. They are designing and building a blended wing or wing body aircraft, large size, 200 seaters or similar cargo capacity, that has those blended wing designs. They have a lot more volume just by the nature of it. Yeah.
And even if you make it liquid, is it still pretty light? Like, is it still mostly a volume question and not a weight question?
Yes, absolutely.
And one other question about liquid hydrogen. If you have a canister of highly compressed liquid hydrogen, don't you effectively have a bomb? Like, this is, I think, what comes to a lot of people's mind when they think about this. Aren't you effectively flying on top of a couple of extremely potent bombs?
Yeah, so definitely frequently asked question.
I believe it.
On hydrogen. Actually, in fact, for the first year of ZeroAvia, my second slide in my presentations was Hindenburg slide.
Of course.
Okay, because everybody would ask that question anyway, so I better get it out of the way right in the beginning.
Well, gaseous, not so much, but liquid hydrogen, then you really are. That is a lot of energy crammed into a small space.
Well, the amount of energy, the absolute amount of energy is about the same or half of the amount of energy that you have in the jet fuel in the same volume, right? So about the same if you want the same range, but about half if you put it in the same volume.
Right.
So from the total amount of energy, it's not that different. It's a matter of how you manage this chemical energy. How do you ensure safety?
You could just reply like, existing planes, big fuel tanks are bombs.
Those are flying bombs, yeah?
Right, those are bombs too.
Exactly. So they carry the same amount of energy or more. And in the right conditions, that energy can be very quickly released, as you've, I'm sure seen in some accidents, yeah? And for hydrogen, actually, there are a lot of safety factors that favor hydrogen. And NASA has done some work on it, and some other people have done some work on it. To give a couple of examples, for instance, a lot of accidents in a traditional aircraft, the sequence looks like this. Pilots are able to get aircraft on the ground. It's a hard landing, or it overruns the runway. Fuel tanks get ruptured. You have fuel leak. It ignites, and there are tragic consequences. Yeah. With hydrogen, you cannot have a leak that pulls on the ground. If you have a leak, if you have a tank compromise, let's say a crack in the tank, for instance, you have a leak that immediately dissipates up in the air.
Right. But we should say spewing hydrogen directly into the air is a pollutant. That is bad for the...
That's right. Obviously, an emergency situation. Yeah, you don't want to do it, right?
Right.
But it doesn't kill everybody.
Right.
So, obviously nobody wants that to happen, and it will not happen with any kind of frequency. But if it happens, then the properties of release of fuel are such that it's much less dangerous. And it has actually been shown. There are some interesting videos from, I think, Department of Energy, actually, tests of hydrogen car fires versus gasoline car fires. And with temperature sensors in the cabin and all those things, and how things are affected, and it's a pretty dramatic difference.
Yeah.
In favor of hydrogen in that case.
It is kind of funny how paranoid people are about it, given the fact that we're all always riding around with giant tanks of flammable fuels in close proximity,
But this is how people are, right? So remember when Tesla was putting first cars out there, every Tesla fire was like a worldwide news.
I mean, still, it is kind of a little bit like that.
But it is super rare. It is super rare, relatively speaking. And on hydrogen, last thing, we have right now maybe around 100,000 hydrogen vehicles, ground vehicles, between cars, trucks, buses, forklifts, all that. And you don't hear about hydrogen vehicle fires. And you would hear about hydrogen vehicles if they were happening, okay? And you don't, because they don't happen.
All right, so let's talk about then innovation in fuel cells. So fuel cells, the category of fuel cells is very broad. A lot of different fuels can go in, a lot of different designs. I'm assuming for this very specific application, you're designing your own fuel cells and innovating on your own fuel cells. So what is the sort of path for innovation on the fuel cell side? How do you get more out of that?
Yeah, correct. So specific designs, especially for larger aircraft, and larger is already, these large propeller planes already require significant modifications and new designs. And then when you get to jets, it gets even harder. So the direction of research and design is moving to higher temperature fuel cells, which require material change. So it's not just, hey, let's crank up the temperature. You have to move from some of the materials that we are using today in fuel cells to new materials. And we have that design and development in-house.
Is it just that the chemical reaction is more efficient in higher heats?
Yeah, it is a little bit more efficient. Yeah, you increase the temperature generally. Chemistry likes temperature increase. Things happen faster, more efficiently, in smaller volumes. And importantly here is it's much easier to cool higher temperature systems than lower temperature systems. So let's say you have 50% or 60% efficient fuel cell. This means that 40% of the chemical energy that you feed from hydrogen transfers to heat. It is much better, much lower level of heat than in combustion engine, but you still have a lot of heat and you have to remove it. Now, if you are operating like traditional fuel cells in the cars, for example, and the type that we have in the first engines, if you're operating at about 90 degrees Celsius, and you're sitting on the tarmac at Phoenix Airport, for example, or even worse, Abu Dhabi, for instance, in the summer, your difference between the 90 C temperature of the fuel cell and, let's say, 50 C ambient temperature is quite small. So it's just 40 degrees difference that you have to move the heat out of your fuel cell. Now, if you increase the temperature of the fuel cell to about 200 C, and this is our high temperature fuel cells that we're developing in-house, then your delta T, or the difference in temperature, goes from 40 degrees between 90 and 50 to 200 minus 40 minus 50 or 150 degrees, which is almost 4 times larger difference in temperature, your cooling becomes 4 times easier. Okay?
Why is cooling easier when you get hotter waste heat?
Yeah, because it's like when you boil water, right? If you have boiling water and you look at how quickly it cools from 100 degrees down, you will see that the first 10 degrees are much faster than the last 10 degrees. Yeah,
right.
Because when it gets closer to ambient temperature, the heat flow rate slows down dramatically. And mathematically or physically, you never get to the ambient temperature because it's asymptotically, slower and slower. So that hurts the lower temperature fuel cells. So you need to increase the temperature.
And can you also increase efficiency and thereby just get less waste heat?
Yeah, you get a little bit of increase in efficiency, and you get increase in efficiency also from the system side. It's a little more esoteric, I guess, a nerdy discussion, but because you have now hotter exhaust, you can use that heat. Also, you can recover some of the energy from the exhaust heat as well through a turbine. So your compressor becomes sort of this compressor turbine combination that it's almost like a turbocharger on your car. Right?
You're using the waste heat to compress the air, which is...
That's right. You use part of that energy to add to your compressor. So you need the smaller compressor drive and you save some energy there and your system becomes more efficient as a result.
And do we have any sort of like target efficiency? Or you say like current ones are in the 60% efficient range. Are there theoretical limits here, or is there a target efficiency?
Yeah, the theoretical limit for a fuel cell is, I believe, around 94%. That's the theoretical limit. So it's quite high up there. Yeah. Now there are, obviously several reasons why, we're not at theoretical level or nobody's theoretical level. But there are fuel cells out there that already operate in the 70s at relatively low power levels. So we are obviously cranking them up at quite high power levels. So there is some work to do. But it is a material challenge, mostly in the conductivity of various coatings and membrane materials.
So for the fuel cells, it's a materials science challenge, mostly. Interesting. And you guys are doing all that in-house? Like, is there are you able to draft it all on broader scientific push in fuel cells? Like, are a lot of other people working on fuel cells?
Yeah, definitely. There are, on the high temperature side, there are probably 3 companies, including ourselves, on the top of the field. And then there are some sort of tier 1 partners that we're working with, like BASF, for example, is a big German chemical company. And they're working on some membrane materials that we're utilizing. We have a joint venture or joint work development with them.
And do you lose any of the safety benefit when you introduce high heat back into the mix?
Not really, because high temperature is still, very low temperature compared to combustion, right? We're talking about 200 degrees versus almost 2,000 degrees of combustion temperature in the combustion. So as a result, we can use simplest materials still, like aluminum, for example, which is cheap. It's very formable. It's very heat conductive and electricity conductive. Versus, turbine engines have to grow single crystal turbine discs out of Inconel.
So the last piece here, so we got innovation in the hydrogen, mainly compressing it into liquid is going to be necessary for the bigger planes. We got innovation on the fuel cell side, trying to increase the temperature of the fuel cell process, increase efficiency output there. And then the other piece is the electric motors and rotors. Now, this is a question I always have about electric motors. Like, at this point in things, there just have to be like gazillions of people working on making electric motors better, right? I mean, these are everywhere. They're getting more and more ubiquitous. They're doing more and more things. So there just has to be like a ton of work happening here. Like, what is your piece of of that? Are you personally trying to make electric motors better, or are you focusing on sort of the plane specific parts of it, like the rotor or the propeller, or what's the innovation on that side of things?
Yeah, your intuition absolutely right. This is I would say, the least complicated part of the equation for us.
Right.
Yeah, we do have to, design and build our own motors or aviation specific motors, but that mostly is because the design process for aviation certification is different, and you kind of have to start from scratch to do it. But the principles are the same.
Right.
If anything, at some point in the future, maybe when we get to the largest engines out there, let's say similar to what drives a 787, we're even beyond the single aisle. That's when people start talking about maybe cryogenically cooled electric motors with superconducting, windings and things like that. But really, it's not even required. If you think about the kind of challenges between the current state of technology and where you would need to go for these large aircraft, the biggest challenge is in the fuel cells. The second biggest challenge is in the fuel tanks, fuel storage, and fuel system. And the last, sort of the smallest challenge is in the motors.
Interesting. Very interesting. All right. Well, we're running out of time, but I got two big questions left. This is all just super fascinating to me. So let's talk a little bit about right now. When I started reading about you, the company, when I found out that you're just swapping engines in existing planes, I thought that seems kind of crazy because in like the EV space, like, the reason EVs are working is that they're designing lighter bodies and stuff around these engines so you can just go farther. Like trying to take a big old heavy metal, existing combustion car and lifting out the engine and putting in an electric engine is just like you're just setting a very high bar for the difficulty there. So it seems like you're doing difficult things trying to lift these heavy planes. And I just wonder, are people, I mean, I know people are out there designing new kinds of planes around electric propulsion systems. And I know this is probably that's like a whole podcast in itself, I'm sure. But like, what could you say briefly about just sort of like, what does that look like? And are you working with specific designers making specific planes around your specific propulsion system?
Yes, very good question. And yes, we have some clean sheet projects as well. I think 3 or 4 at this point. A couple of them are public.
And these are like different, fundamentally different design ideas about it.
Yeah, it's different materials. Sometimes different materials. Mostly, a lot of composite materials.
Carbon nanotubes or whatever.
Yeah, mostly, and there is a bit about structural integration of components. So you can use, for example, the compressed hydrogen fuel tanks are likely the strongest components of any airframe you would integrate them into. Okay, because these are basically almost 1 centimeter thick carbon fiber shells to contain the high pressure.
So you can make them like load bearing. You can make them do work. That's interesting.
You should. You should, right? Because again, this is the strongest part of your airplane. So you can, for example, there are some concepts that say, well, why don't we build wing spars out of those things? These are basically a structural element that keeps wing, its shape. Yeah.
Right. So you'd be kind of putting hydrogen into the wing then, rather than like into a discrete tank.
Yeah. So there are a few projects like this, but those take longer time.
Of course.
Because you have to design the aircraft, you have to design the propulsion system, you have to integrate, then you have to certify the whole thing.
Yeah, I assume the FAA I assume there are lots of hoops to jump through when you're coming up with a brand new plane.
Exactly. So my big vision here is to transition the entirety of aviation to this new type of propulsion. But the first transition, in however small the aircraft is, commercially viable, commercially relevant aircraft, is going to be a huge step.
Yeah.
So what I wanted to focus the company on is to say, all right, what's the smallest relevant scope that we need to take? And it will already be huge amount of work, but what's that scope that we need to take in order to jumpstart that transition? And it turns out to be engines initially for existing aircraft, because then I don't have to prove to the regulator that the aircraft is good.
Right.
That's already done. I just need to replace the engine. And by the way, replacement of the engines happens all the time. in the industry, yeah, because new engines become available and manufacturers say, okay, we're going to re-engine the aircraft. We're going to certify what's called a supplemental type certificate for the aircraft with a new engine. That's being done in the industry. So I'm writing the existing processes in the industry to do it. You mentioned automotive as a comparison. As we talked, I think in the middle, a typical airframe outlasts several sets of engines. So as a result, these markets are different. These very structured market are very different.
The engine market and the plane body market.
That's right. In automotive, there is no distinction.
Right.
Yeah, because everything is monolithic. Yeah. Here you have, even if you look at the companies in the aviation space, you have aircraft manufacturers and they don't make engines. Okay. And you have engine manufacturers, they don't make aircraft. Okay. Because these two are different. And even you go to operators like airlines, like United, American, and all those people, they buy their aircraft from Airbus, for example. They buy their engines separately from Rolls-Royce and the others. And yes, they come together at the factory, at the Airbus factory, but these are different contracts.
Interesting. So you have no plans to become a plane body maker. You're just going to put these engines, but you assume, like, I guess the plan here is like you put a bunch of these in small planes, a bunch of small planes fly around with them. Everything's fine. It shows people it can work. And then sort of like that flywheel accelerates a little bit. And you expect other plane body makers to start sort of designing to this?
Yes, absolutely. And we already have some projects like that. And we hope to become the largest designer and manufacturer of this new generation of propulsion for aviation.
So then in this bright future, you're hitting, you talk about sort of like hitting kind of the limits once you get up to like a single aisle plane. But if you could design even larger jets, like if you could design the full size jets top to bottom around electric propulsion, just so they're lighter, maybe different shape, maybe wing body, whatever it is, theoretically, you could get the biggest planes on hydrogen, like in the future, if you combine innovation in the engines and innovation in the bodies.
Correct.
So there's no remainder in your mind. There's no part of aviation that's out of reach of this.
That's right.
Well, that's happy making. We're sort of out of time, but I did want to ask you, like this again is another huge topic, but just like we say just a few words on it. There is, people who talk about electric aviation, generally these engines, quote unquote engines, today at least have less range. And so kind of the parallel conversation that goes along with electrifying aviation is restructuring how and where people fly. Because right now, like there's a lot of, this is sort of one of the things I learned from Kyle, is a lot of like packages, you go on a big jet and you take a very circuitous route to where you're going because you're flying to big airports, basically. So if you had just smaller planes, you could have a lot more airports. They wouldn't have to be as big and they could be spread out more and you do a lot more short hops. But then for your vision to work, you also have to throw in refueling, which is when it comes to highly compressed liquid hydrogen, not necessarily a small thing. So maybe just say a few words about how you envision kind of the air system, the airport system, the flying system evolving around this.
Yeah, we definitely see a lot of this, like Kyle mentioned, and I know Kyle and very good company. Probably one of the most practical new aircraft companies out there.
Love that guy. One of my favorite pods I've ever done. I love talking to him.
Exactly. So I think I agree with him that we are going to move more to point, a lot of smaller locations, a lot of the connectivity improvements in the smaller communities through this, partially because of the much better economics of the small aircraft on electrified propulsion versus on fossil fuel propulsion.
Is that just like less wear and tear, less less
maintenance? Right now we're super early on the hydrogen journey.
Sure.
For this, and if you look at the fundamental economics of green hydrogen and renewable hydrogen, your marginal cost of the molecule wants to go to zero, meaning that we already have this with renewable power. Yeah, you put a solar farm, and the incremental cost of any after you put a solar farm in, incremental cost of a kilowatt hour coming out of those solar panels is pretty much zero, right? You need to clean them periodically. You don't use any fuel. For electrolytic hydrogen production, it's the same, because it's almost like a fuel cell. You don't have any moving parts. You put capital expense in, and then it just works for tens of thousands of hours.
And you're talking about electrolyzers.
Yes.
So you envision like these smaller regional airports having hydrogen electrolysis on site.
It doesn't have to be on site at every airport. So we have this concept of airport clusters. And as I mentioned, right, we sold already thousands of these engines. Every time we go to the operator and make those deals, we actually study their networks, and we build the fueling network as well, or plan for the fueling network. So we have this concept of clusters of the airports that tend to be sort of within, let's say, a couple of 100 miles radius. And there is a anchor production site within that cluster that we start with. And then you produce there, and you can deliver to the other airports. And as the traffic grows, then you can put one more production site in that cluster, and then you go from there, right? But you don't have to have production at every single one.
Mm-hmm.
So you move to the network that is much more local, much more point to point, and generally smaller aircraft. And in fact, actually, we've seen that already in the in the current aviation market over the last 10, 20 years. We've seen that movement already. Yeah.
Just for operational reasons, savings?
Well, people like to not connect, because it's shorter.
Yes.
Yeah, it's less time, and as you grow the traffic density, you have more and more opportunity to go direct. And you see, 20 years ago, A380, right, the biggest aircraft out there, was a big deal. 747, a large aircraft, was a big deal. And now those aircraft don't really fly, we don't produce them anymore, and they're being phased out in favor of aircraft like 787, 737, which going direct to point to point. So we're already seeing that, and electrification will accelerate that move.
And I'm assuming like electrolyzing hydrogen is electrolyzing hydrogen and hydrogen. So there's a lot of people out there who are thinking about electrolysis and working on electrolysis of hydrogen. Are you messing with that at all? I did see one press release where you are working on some kind of AI to improve electrolysis. Like, are you getting involved? Like that's a whole industry to itself. Are you getting involved in that at all?
Yeah, we're not getting involved in the electrolysis technology itself, but the way it gets integrated into these on airport production assets, because it's connected to the aircraft and to the airport environment. We know a lot about it. We actually built already 3 locations at airports, our own fuel production.
Oh, interesting. You are electrolyzing hydrogen for yourself now already.
That's right. Now, we, of course, buy electrolysis equipment and all that. Sure. We don't make any of that. But what we do is that we put it together at the airport with a little bit of battery capacity so that we buffer energy, with a little bit of renewable capacity, and connect it to the grid. And then we can manage the production of hydrogen so that hydrogen comes out at a lower cost. In that segment, we see ourselves as kind of building the blueprint of how this should be done, and then offloading that blueprint to the energy folks, the utilities, the energy providers out there, so that they can build more of these.
Are you banking at all in terms of your business plans, et cetera, on substantial reduction in the cost of electrolysis, or is that just kind of a fixed quantity for you?
No, we expect the electrolysis cost to go down quite a bit, but already today we have, I think, definitely more than 10 contracts. I think it's around 15 or so, and growing worldwide on supply of green hydrogen from various producers at the costs
at airports
that we can deliver to they deliver, or we can deliver to the airports. Yeah, close enough. Yeah, so it's not uneconomical. But the point is that the costs that we're able to contract are already getting to break even with jet fuel.
Oh, interesting.
Yeah. And partially, we are able to do this for aviation, especially for small aircraft, much sooner than for cars, and definitely sooner than for heating, because of much higher efficiency difference. Yeah, and aircraft fuel is not cheap. It's a relatively highly refined fuel, and it goes through all kinds of controls and everything, so it tends to be relatively expensive. So it's easier to break even against that. Much easier than, for example, for a diesel truck that has a very efficient Cummins diesel engine, and diesel cost is relatively low. So a break-even situation is much harder for hydrogen over there compared to aviation, small aircraft.
Goodness, this is a lot to chew on. Super fascinating. I hope maybe next year I can take a zero carbon flight. That's when you envision the timeline of making it all the way up to Boeing 747, say, the single aisle jets, like when ideally in your plans, when is that? Is that like in my lifetime? Am I going to be able to fly a zero carbon passenger flight between two major cities before I die?
Yes. So I think from the technological perspective, we will have the technology to power a 737 size aircraft, which is 250 seat aircraft in around 10 years.
What a time to be alive. Okay, well, we could go on forever, but this has been super fascinating, tons to chew on. So, Val, thank you so much for coming on and walking us through it.
Thank you, Dave. Appreciate it.
Thank you for listening to Volts. It takes a village to make this podcast work. Shout out especially to my super producer, Kyle McDonald, who makes me and my guests sound smart every week. And it is all supported entirely by listeners like you. So if you value conversations like this, please consider joining our community of paid subscribers at volts.wtf, or leaving a nice review, or telling a friend about Volts, or all three. Thanks so much, and I'll see you next time.